Good afternoon, good evening, good morning to everyone who is with us today from around the world. We really appreciate your attendance and you taking this time out of your day today to be with us here as we talk about this very exciting topic and discuss basically to me, which is one of the most exciting new technologies and sciences to come from remote sensing. So this is continuous space-based surveying and monitoring for detecting millimeter movements on the ground. So once again, we really appreciate your time and we look forward to what's going to be an excellent webinar. To begin with, I'd just like to cover some important housekeeping notes. So it's very important to understand how to engage with our team. So all lines will be muted during the presentation. However, if you have a question at any time during the webinar, please use GoToWebinar's questions panel. So you can find it in the bottom of your window here. You can just expand this area and then you can type your questions directly in here. We will then use those questions during the Q&A session in order to answer the questions that you ask. So once again, if you have a question at any point in the webinar about something we're discussing, please feel free to put it into this questions panel and we'll do our best to get to that question during the Q&A session. To begin with, I'd like to just begin by introducing our panelists and the webinar presenters today. So first off, we have Gabriel Gosling, who is our senior InSAR scientist and team lead. Please introduce yourself, Gabriel. I think Gabriel might be muted at the moment. So we're just going to hand things up.
Can you hear me now? Yeah, okay, sorry.
We can hear you, no problem.
So I was saying that I've been working in the remote sensing industry for more than 15 years with a specialization in SAR technology since the beginning. And my background is really with the use of SAR polarimetry for environmental monitoring. In 2013, I joined Catalyst as a senior scientist. And for the past, I think 3 or 4 years now, I've been focusing mainly on InSAR algorithm developments and InSAR applications. Yeah.
Oh, wonderful. Thank you, Gabriel. And next we have Jason Flatt, who is our solutions engineer and no stranger to these webinars.
It's great to be here, and hello to everyone who's seen me before, and welcome to those who have not. I'm excited to be here. Just a brief intro. I've been working at Catalyst for just around 3 years, and I've had the pleasure to work with a number of different SAR and radar-based projects. So really excited to be here and presenting.
Wonderful. Thank you so much, Jason. And myself, finally, I am your host. So my name is Sean Malamed. I'm our product marketing manager here at Catalyst. So once again, on behalf of all of us, we'd really like to thank you for spending this time with us here today. So without further ado, I'd like to jump into our presentation and we'll begin the webinar, the actual material. So here at Catalyst, our goal is to make actionable Earth observation intelligence available to decision makers that seek to ensure a sustainable and manageable planet. So the product and solution we're about to show you today, I think really embodies this mission statement of ours. Before we go into that, let's just discuss very briefly some of the webinar agenda. So we have, we're going to quickly provide an overview about our new web application, which is called Catalyst Insights. We're then going to go into the meat of the presentation and discuss our deformation mapping capabilities, looking at a demonstration, details, and theory behind it. And then we're going to conclude today with a question and answers period where we're going to scan the different questions that are posted into that Q&A session of the webinar, GoToWebinar, and answer as many questions as we can. So I'm going to begin by just providing a very brief overview of Catalyst Insights. So it's a new product introduction that we've just recently launched. So Catalyst Insights is a very simple web-based application that provides an information service where different users such as decision makers and end users can subscribe to in order to get actionable insights from Earth data. It's designed to be a very simple solution to use which is meant to attract both geospatial experts and non-geospatial experts alike, which is going to make the information more readily available and accessible to everyone, but making sure that we're still providing meaningful insights. So the way that it works is really as simple as 1, 2, 3. So we're going to have one, you have to subscribe to an area. So you can just select the area that you wish to subscribe to, whether it's a large coverage, such as an entire state or a country or just a very large geographic region. You can have localized areas that can be very small regions, such as construction sites, mining sites, bridges, different particular areas that you want to perhaps monitor, perform some form of analysis on. It could be corridors. So this is a very popular subject already within, since we've launched Catalyst Insights. So corridor mapping and monitoring of, say, oil and gas pipelines, of key hydro and power infrastructure, as well as road networks have been another topic that's been commonly discussed. And then as we go forward into the next step, so after you subscribe to your area, you then have defining your settings. So you just define your subscription parameters. So these could be things like the measurement details that you need to obtain, the frequency. So how often do you need these measurements to be updated? Different alerts and thresholds that you can set to determine when is the system going to reach out, or what do you want to be alerted to? And then from there, you would simply review the subscription details, the payment details, and then after you've accepted it, you can then access the information within the parameters of your subscription. So you'll have access to alerts. So as soon as one of the conditions are met based on your alert settings, you'll get an alert. You'll have in-app access to the information and presented in a variety of ways, both digital and numerical, as well as through graphical interfaces and graphical visualizations. And then, of course, we have ways for you to get the data into out of the system and into, say, your own internal systems, whether it's your ERP, whether it's your BI solutions, GIS solution. So we can integrate and get the and export the information from our Catalyst Insights platform in a variety of different ways that we're actually going to show you today. So furthermore, with Catalyst Insights, so what we're doing here with this product is that we're building a collection of subscription-based information web services that leverage Earth observation data. So we're going to be, and so stay tuned, we're going to be announcing a number of new information services over the coming few months. But the one that we're going to be talking about for the rest of this webinar is our deformation mapping solution. So this is our solution where we can basically identify that millimeter level ground movements using radar, space-based radar imaging. So at this point in the presentation and the webinar, we're going to move into our demonstration and then discuss some of the details in theory about deformation mapping. Before we go into the demonstration, just want to once again very quickly provide an overview about and an abstract about what this service is. So our deformation mapping web service provides global access to historical and near real-time ground deformation measurements, sensitive enough to identify movements as small as a few millimeters. So to me, that's still a little bit mind-boggling that from hundreds of miles away, we can detect movements as small as a couple millimeters, but we're really excited to show you what we can do and a bit of insights into how we can do it. So with that, I'm going to hand things over to our solution engineer, Jason Flatt, who is going to provide us with the live demonstration of Catalyst Insights for deformation mapping. So with that, I'll take it away, Jason.
Thank you very much. Hello, everyone. So what I'd like to be demonstrating today is how a user can utilize Catalyst Insights to analyze Earth observation. Let's say I'm just going to turn on my webcam as well. Earth observation data combined with other non-EO data to support decision-making as it relates to infrastructure for this example. The results we're going to see have been generated using Sentinel-1 imagery processed with our own workflows and analysis technology. This example is for a customer who works for a power utility and is responsible for monitoring the distribution across the state. Since some of the infrastructure is underground, understanding the stability and risks associated with subsidence is key. Any interruption and downtime in the service will have a direct impact on the revenue for the utility, not to mention having to repair the infrastructure as well. So as a result, a prescribed maintenance approach can alert the user if any unusual issues arise that may affect the system. So with this prescribed maintenance approach, I'm going to be alerted to any deformation alert, So I'm just going to get out of PowerPoint. I've already been notified by an email from the alert. I'm just going to open up right here. And this tells us that there has been a deformation change, giving us the level of deformation, the coordinates, the unit number, and a bit more, and a number of pieces of information for details. Wonderful. So now let's actually take this into Catalyst Insights and see this alert location. Close that and open it up. Perfect. So what we have here in the information viewable in the service, we can see the alert location and its associated transmission lines. The alert location is that red dot. And that's been based on the notification. So now we need to analyze the deformation measurements to determine if I need to, or the user needs to send a maintenance crew to check the location. What I'm first going to do before zooming in is to load a time series analysis or a time series layer to just showcase the general trends, which I'm going to turn on, and that are occurring in this region. Now, important note is that there's a significant amount of deformation occurring due to aquifer deficit caused by large scale agricultural usage, population growth, and unfortunate droughts occurring in California. So what we see, these red areas are showing over the course of 4 months. What this time series shows is that red areas are areas of high deformation. In some areas, it's actually 45 centimeters or more. So we have an understanding now of what the general trends. So I'm going to turn it off and now zoom in to the location. What we can see, the alert is at the end of a transmission line, and it is providing energy to a large-scale industrial complex. So it's very important that we monitor this and we're alerted to check if we need to send out our maintenance crews. What I can first do is to turn on a parcel layer risk information layer, which identifies the current risk based on the latest data that was created, that I was notified based upon. I can hover my mouse, and we can see it's a risk level 3. Now, these risk levels can, of course, be configured based upon, or notifications in general can be adjusted based upon and represent what you, the user, requires. For this, the risk level 3 represents any deformation between 0.3 and 0.4 centimeters of change a week. So now I can turn off the layer and open up the cumulative displacement. This is finally to get a more detailed look at by displaying point data that was derived from the space-based surveying. Each point, I'll hover over the one closest to the alert location. Each point contains a cumulative displacement for the interferometric pairs. And what we have here is we have the ID, the latitude, longitude, and 5 measurements of displacement over the course of 2 months. Now, once with that, we can then identify, if we look at other areas, that their amount of change occurring is around 2 centimeters, and there's a uniform trend actually. I'll go to maybe a few more points. But let's actually analyze it in a different way. So let's take a further step to analyze the area. And what I want to do is capture the surrounding information, determine what my next step actually should be. Should I send a maintenance crew or should I not? So this information can be exported from the visual interface. I can just select a few points. Let's choose 4, for instance. This can either be extracted from the visual interface or utilizing the Catalyst Insights API, which can be then integrated into an external system for analysis. Another thing to note, we can view this data as well in the system itself or in the Insights window as well with this table. But what I've done is I've actually synced it with a third-party system, Power BI, for these 4 points. And I'm going to view that right now. And what we see, a trend line for those 4 points, and between utilizing the entire data set, the archive, covering images from September 2018 to February 2019. What we see is there's a trend of cumulative deformation that's going down, of course, due to the aquifer usage. But what's important to note is let's select the individual points themselves. So I'm going to choose the first one. We can see it's blue, purple, orange, I guess purple or blue. So what this shows us is that there's actually a uniform trend going down. If we saw any differences between the two, or between the points themselves, between the measurements, then the deformation would not be uniform, and that is important to note as well. So with this uniform trend, though, we don't need to send a maintenance crew in. So in conclusion, what we've seen here today is that a user can leverage prescribed maintenance approach to decide whether a maintenance crew needs to be sent for further investigation. What we've done is, after reviewing the information at the displacement around the power station, as it is uniform, there isn't a major risk to the location. But of course, in the inverse, if we did see differences in the points that I selected, it would be wise to send a maintenance crew for further investigation. Back to you, Sean.
Wonderful. Thank you so much, Jason. Okay, so just to summarize what Jason showcased to us today is in the demonstration is he explored the Catalyst Insights web interface. There's much more to it as well, but he just showcased some of the key attributes as it pertains to this specific demonstration. He also showcased a prescribed maintenance approach, or a demonstration around prescribed maintenance for monitoring infrastructure. He leveraged historical and near real-time ground movement measurements from Sentinel-1 and used our alert system in order to be alerted to a potential issue where you might need to sound ground units to further investigate, and showcase some of the different capabilities for viewing, visualizing, exporting, and integrating the ground deformation measurements and information within Catalyst Insights, as well as between Catalyst Insights and third-party systems. So wonderful. Thank you so much again. So at this point, we'd like to engage with our audience and take this opportunity to just ask a survey question. So with this one, the survey question, so I'll just launch it in just a moment, is what do you want to do with deformation measurements? So I'm going to launch it now. So you should see it on screen. Or what do you want to use deformation measurements for? So do you want to use it for monitoring infrastructure? Is it for mining applications, construction applications, monitoring slope stability, or is there something else that we didn't list? In which case, we'd love for you to let us know in the question and answers panel of the GoToWebinar. So I see all the answers are flowing in now, so we'll let you just take a few moments to get and submit your answers. And also, feel free to check all of the different options that apply to your case. So once again, I'll just run through them. We have mining, monitoring infrastructure, construction applications, monitoring slope stability, or other, in which case feel free to answer or provide your information into the questions and answers panel. We would love to know what you'd like to use this information for. Okay, so we've about 3/4 of the people on the webinar have voted already. So we're just going to leave the polls open for another, let's say, 10 seconds, in which case we'll close the poll. So please get your answers in now if you can. So we'll just give it another 5 more seconds. Okay, 3, 2, 1, and I'm closing the poll. So really appreciate that. I'm going to just share the results here. So you can see on your own screen that about 24% of you said mining, 45 monitoring infrastructure, and that's kind of based on a lot of the conversations we've had since we launched this. It seems to be a common thread. 29% said construction applications, 56% said monitoring slope stability, which is probably one of the more common applications, and it's used throughout. And then 21% something others. So hopefully you're able to put your application into the question and answers panel. We'd really love to know once again. Okay, so with this, we're going to move on through and go into some of the details behind how we get those points as well. So part of the Catalyst insights for deformation mapping, so some of the value that we see, and from just talking to some of the customers and working with a variety of the different industry partners, is that it can really help reduce risk of operational downtime and failure. And this really came, actually, we were talking to a partner yesterday who works very closely in the mining industry, and it's become mandated throughout much of many different countries now since the mining collapse of the tailings pond in Brazil occurred, that now it's mandated to have improved monitoring and risk assessments on these tailings ponds. We're seeing a major uptick in the use of InSAR for these applications, but there's so many more applications like highway safety, so improving public safety, worker safety on construction sites by checking for potential unstable slopes, improving public safety by making sure highways are clear of potential other landslides and issues, and infrastructure is a huge one, of course. So just making sure that the uptime and prevention of potential failures occurs or doesn't occur. Sorry about that. And third-party validation. So this is another great application that we see with working with municipalities or other organizations that just want to monitor what's going on around them. So if there's pipelines or key infrastructure going in and around your particular vicinity, having that ability to just monitor it using your own data to make sure that you can have some checks and balances on the surveys that are being performed by different groups. So what is available on Catalyst Insights for deformation mapping, and what can you do with this service? So we provide on-demand access to historical ground deformation measurements for most of the globe using Sentinel-1, as well as a growing list of commercial sensors. And you can access this by subscribing in order to access the historical and near real-time information, and then get these kinds of alerts like what Jason showcased to you today. At this point, I'd also like to just quickly talk about the science behind the simple. So this is how are we making it easy for geospatial and non-geospatial users alike to be able to access this information and integrate it into their own internal systems. So it really works like this. One is you provide the requirements. So it might be things like budget, area, dates range, frequency of measurements, and so on and so forth. So you provide the requirements of your project, essentially. And then from there, we can take that information and then we will optimize the details. So we will help you, and the system will help select the most suitable sensors, like what data should be used for the application that you're trying to use. And one of the other things, because we're working with a variety of different data providers, we also have the ability to select multiple sensors. So perhaps you have a frequency of repeat measurements that you need that require us using multiple sensors. So that becomes also possible within this platform. The other thing is the workflow settings. So once again, based on your requirements, based on the application that you're doing, we can optimize the workflow settings based on making sure that we're providing the right kind of measurements for your application, the right kind of accuracy, the right kind of density of points, right kind of frequency, and so on and so forth. And then finally, the quality assurance is that's one of the other benefits about this being an information services, is that you can also ensure the quality is there, and we're continuously, and we'll talk about this in a little bit, but we're constantly validating the technique in a variety of different studies. Okay, I'd like to now move into the science behind the measurements. So before I pass things over to our senior InSAR scientist, I'd just like to quickly mention two things as he discusses these two key concepts. So we are leveraging InSAR and so SAR interferometry and persistent scatter interferometry. With regards to SAR interferometry, what's really important to take away from this is that the SAR interferometry is the technology that is used to detect millimeter ground movement whereas the PSI, the persistent scatter interferometry, is the technique that's used to ensure the accuracy and the reliability. So as Gabriel goes through these concepts in a little bit more detail, keep those two things in mind. So with that, I'm going to hand things over to you, Gabriel. Thank you.
So can we go to the next slide? So yeah, the classic, how can I say, the classic interferometric process is a 2D process where you have a pair of images, and from there you have to remove different effects like the topography effects. You have to remove for the flattered phase, also due to the curvature. You have to reduce some the atmospheric component. And since the waves travel at the speed of light, and we know exactly the distance between the sensor and the ground, you can, if you compare two images, you can easily compare the number of cycles that the wave went through, and then this is where you can measure millimeters accuracy between two images from an interferogram. So, and this distance is from the line of sight. So if the ground is moving down or moving up, this is something that can detect because you have a perfect control over the wave that have been emitted from the sensors. And can we go to the next slide? One of the problem with the classic interferometry, which I call the 2D mapping, is to have a reliable phase unwrapping. Usually you will have to average a lot, either like especially by doing a multi-looking or by applying a ghosting filters. And you can always use low coherence mask. One of the problem with this approach, which is really good for like extended natural area deformation, is when you're doing urban monitoring, usually, or not only urban, but infrastructure monitoring, you want to be at higher resolution and to have more reliable measurements. So one of the techniques that have been developed in the past, I'll say decade, and one of the technology that is behind this Catalyst Insights for deformation mapping is the persistence scatterers interferometry. So the way it works globally is you create a stack of 15, 20 images, 25 images, and you compute the amplitude dispersion. So instead of trying to process the entire image, you will only typically process 2 or 3% of the pixel of the image, and those pixels correspond to what you call a persistence scatterer. So you only analyze those pixels and forget about the rest of the image. So those pixels or persistence scatterers are deemed to be very like stable and with a high coherence. So the phase, you can extract more meaningful information from it because you avoid like all this low coherence area. And then based on those time series, you also have to remove some atmospheric effect, and you also have to unwrap the phase at the point level, not in 2D anymore. So now you can measure your ground movement. So you can have persistence scatterers that are not moving at all, no subsidence, no movement toward the sensors. You have other persistence scatterers that shows no change of phase. And sometimes you might have also in the set some persistence scatterers that doesn't show like really typical behavior or can be too affected by noise, and then you don't consider them as a persistence scatterers. But the thing to remember is behind this insights technology for InSAR mapping, this is really the persistence scatterers workflow that is behind this. And after that, as you saw in the web application, this is always possible to interpolate between the persistence scatterers to get a 2D deformation mapping, a 2D deformation map if this is wanted. So I think is giving back the presentation to you, Sean.
Wonderful. Thank you so much, Gabriel. Yeah, so that I hope provides a bit of a background as to how we're able to leverage this wonderful technology. So both the interferometry or SAR interferometry and the persistent scatter InSAR in order to leverage the two. So once again, InSAR gives us the ability to detect that millimeter level movement, and then the persistent scatterers helps to ensure that we have the measurements that we're retaining are of the most reliability, or the most reliable rather. So with that, we're going to move on to the next thing, which is the validation behind the science. So basically, here at Catalyst, and we've been for over 35 years developing remote sensing and InSAR technology. So this is an area that we have been very intertwined within, and have been working using some of the most state-of-the-art concepts, and having access with, along with our partners, or as a result of our partners, the ability to access some of the latest data sets and technology, so we can continue to develop this application. And we've done, as I said, a number of different validation studies. One such validation study was in Cold Lake, Alberta, where we worked partnered with the MDA. This is a little while ago, and we used RADARSAT-2 data in order to measure deformation against, or the deformation as measured, determined by the InSAR approach, against the model deformation based on the geotechnical engineering methodology. And we're continuing to do new validations today. So even right now, as we speak, Gabriel is working with another team, an external team, to do validation using ground truthing, where we're going to be looking at the measurements of our ground deformation measurements that we're able to acquire using our space-based radar, and comparing them to measurements on the ground using more traditional ground-based surveying technology. So before we go into the Q&A session, just like to ask one more survey question. So with this, I'd love to know, how do you hope to use ground deformation information? So I'm just going to launch this poll here, which you should be seeing now. So a couple different options are, you wish to use this information directly within your own organization or within your own work. You want to build and sell solutions with this information, really for educational purposes. You see this as an evolving, important technology, and you want to be able to provide this as an educational service. And then the last one is, you're not really sure yet, you just think it's cool. So I'll give you a few minutes to put this information in. Okay, so we have the majority of people have already voted, so we'll just give you another 10 seconds or so to get your vote in here, and then we'll share the results. Okay, we'll close the polls in 3, 2, 1. Okay, let's see how people voted. So we can see about 20% of the people here use this information, or wish to use this information directly within their own work or within their own organization. 18% wish to build and sell solutions with this information. And 49% are here for educational purposes. That's great. This is an educational webinar. And 13% still not sure yet, but I think this technology is really cool. So do I. All right, so with that, we'll move over to our final section of this webinar, which is open things up for questions and answers. So wow, a lot of questions have been coming in as we've been presenting, so we really appreciate that. Give me 2 seconds as I just pan here and look for the first few questions. So one of the questions I think was asked around the demo. So Jason, perhaps you can help answer this. So the question was, can you please explain why the displacement trends for the different points seem so similar? And I think you did touch on this a little bit in the demonstration itself.
Yeah, of course. So why they're so similar was because they're over near the same location, and they're taking measuring points from the deformation, and we're seeing just the area around it is sinking, but uniformly. If I sample those points and area and those points had different values significantly, then the area wouldn't be uniform, and that could cause some major strain and stresses to the infrastructure.
Wonderful. Thank you so much. Gabriel, I think this one's a really good question for you because we were talking about this earlier. So someone asked, how do movements of slope, how can you monitor movements of slope if there is more of a natural ground and you're not able to get a persistent scattering point directly in that location?
Sometimes it's not really possible, but one way, if there is enough like persistent scatterers around this area, let's say this is heavily forested, again, you can always follow what is happening around this particular location and then interpolate the deformation from the point surrounding. But if the region is like heavily forested and there is no really like coherence across a stack and there is lots of amplitude dispersion, you won't get really persistent scatterers right there. And that will be the same if you do a classic deformation mapping. You won't get any like good currents, so the unwrapping won't be very reliable over this area.
Wonderful, thank you so much. So another question came in was asking, so can you combine data from different SAR instruments to create the time series?
This is something very experimental. I saw a couple of papers, but this is actually more at, I will say more like for academics or research level. This is not something really operational, as far as I know. Yeah.
Exactly, and I think this actually comes from something that I mentioned earlier too about how we could potentially use data from different sensors depending on your needs. And what I meant from that is that we could create multiple time series in order to make sure that we get the different measurements in to fill in the frequency that you require. So there's different ways that we can use different sensors, but not necessarily performed in the same or by combining the data into a single time series.
Yeah, I was meaning like doing an interprogram, let's say with a L and a C band, provided that the acquisition geometry is the same or nearly the same. Yeah, this is something that people have tried and with some relative success. But yeah, you can have a stack, let's say, of Sentinel-1 data for a particular location for maybe a couple of months. And the thing is, independent of the frequency, at the end, you will convert this into a unit, let's say centimeters per year or centimeters per month or millimeters per year. So if you have another sensor that covers another period or maybe the same area or just an area beside, as soon as you convert it at the end to the same units, you will be able to have like a more complete time series.
Wonderful.
Yeah, you can combine them in that way, but not process them at the same time to form a single stack. Yeah.
Exactly, exactly. So Gabriel, you're popular today. So another question that came out was, so in order to get these results, you have to rectify a lot of effects on the signal and image. How can you be sure about the millimeter accuracy, or how can you be sure about the accuracy in general? So what things can we do? What things are we doing right now to help ensure provide the reliability and confidence of the results?
Usually in some engineering project where the accuracy requirement is pretty high, you will have a GPS point somewhere for which you know exactly what should be like the deformation at that particular location. So the InSAR technology is it's a proven technology, but usually you will use InSAR technology to fill gaps both temporally and spatially for like classical surveying, which is highly precise, but you cannot cover like lots of area. So you really use like from time to time some surveying technique to get precise location, and then use InSAR to fill the gaps like temporally and spatially.
No, that's wonderful, and that's actually a great point because we really do see this, especially as it becomes a more people become more familiar with this technology and better understand this technology. We certainly see it in its in the more more recent future to be more complementary to more traditional surveying techniques, as Gabriel said, to really fill in those both spatial and temporal gaps where you don't have any data. Okay, I think we have time for, let's take one more question. Now we have, I'm trying to see if I can get a number here, but I think there's over 50 different questions that we have. So what we do, if we didn't get a chance to answer your question, we will follow up. So we post all the questions on our website with the recording. So this recording will be available, and all of the questions that were asked that we were not able to get to will also be posted on our website with this recording. So if we didn't get to your question, don't worry, we will. So let me just go through. Okay, so actually we'll take a couple more questions. So is there any additional device that needs to be installed on Earth in order to do this? So this is kind of the whole point about this, is that it's designed where you don't need to install another instrument in order to receive these measurements. Now there is instruments that are used, and we've used this in our validation studies to validate the measurements and to make sure we're getting those persistent scatter points like corner reflectors. But no, you don't require any additional equipment that needs to be installed in order to get this information. I'll take one more question. So this one is why those deformations are not visible to human eyes. How does building structures sustain such deformation? So I think this is more just general about the application. So these deformations are, that's kind of the point about why we're doing this, and why this technology is so important, is because these deformations aren't easy to identify. So we need to have instruments and techniques that are sensitive enough in order to look for these movements that can be characterizing a more potential issue that can be happening down the road. And as Jason showcased in the demonstration, a lot of times there'll be deformation of the ground that's happening in a more uniform situation in a smaller area. So that's not always what people care to see. If it's very uniform, that could just be more natural, especially when it comes to infrastructure. But when you're looking at, say, things like infrastructure, what's probably more important is, do you have one part of the ground that's sinking faster than the other part of the ground? And that's going to cause stresses on the equipment that could then potentially cause downtime, or even worse yet, a full-on failure. So, but there's also, in many other things like in tailing ponds, they're using InSAR technology a lot to look for these minute movements to see if there's any potential weak points which could cause failure, and then that often ends up in a full-on environmental catastrophe.
Yeah.
So
you can also think about like karstic environments like we have in southern US or in Turkey, where you have sometimes sinkholes that are forming. So these are like kind of catastrophic events, but most of the time the process before you get like the sinkhole, you can see deformation on top of the surface. So this is something that is gradual, you cannot really see. But once it's occurred rapidly. So there is some warning system that you can have also in the same way than the deformation in urban areas. It's another example.
Exactly. Okay, this is the last question we're going to take, and then we're going to bid farewell. But basically, the question is, and this is a great one, is the ground deformation data already processed, or is it already processed, and how is it available? So basically the way that we work is some of the data, as we process some of the data, so you can actually go and speak with us, and you can go and check out the demonstration that Jason showed earlier, and actually work with some real data that's been processed. But a lot of the time is the way that we're working with this service is because we have the workflows built and the pipelines built. We can basically, you choose the area, and then it's going to on-demand process the data that you need. And so come speak with us, and we can give you a lot more information about how the system works and how it can be used to, so you can get that historical data, but then also get that near real-time information as the data becomes available. So with that, I'm going to just once again, thank everyone for your time. We really appreciate you being here. We love the engagement, and we look forward to following up with you and providing you with more information. So reach out to us, and we'd love to talk more InSAR and ground deformation. So once again, on behalf of the team, thank you so much for joining us.
Thanks.
Bye.